everybody. Welcome back to Markov Processes. It is week 2 of the semester, but week 1 for us because we had a snow day. And I hope your first week went well with your other classes. But let's get going in here. I put up a review video last week, which is to review conditional probability. I think a lot of you have had that, and I may have even pushed you away from it by saying, oh, it's only conditional probability. If you've had it, don't worry about it. But I did go a little bit further than that. I defined a Markov process, and I'm going to do that again here. But I did go further in conditional probability than you might have gone in the past. So I will do the very briefest of reviews in here because I don't want to slap in the face to anyone who spent the time watching the video. And if today is confusing to you and you didn't watch the first video, then I'd highly recommend going back to it. Okay, let's go. The word stochastic means random, and process refers to something evolving over time. And when you put them together and have a stochastic process, you're talking about a time-indexed sequence of random variables. Now, random variables can be discrete or continuous, and yes, they can be a mixture, but usually in beginner classes in probability, they are discrete or continuous, and time could be discrete or continuous. So when you put these together, there's 4 possible, combinations. There's discrete, 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 continuous, continuous, discrete, and continuous, continuous. And in this class, we're going to cover the first 3, because to do continuous random variables through continuous time, you need stochastic differential equations, which is an entirely separate course. By the way, that's offered from time to time in a PPM. I think it's still on, it might still be on a special topics rotation. So if you want to take it next semester and you don't see it, demand stochastic differential equations. So out of the 3 remaining regimes, discrete, 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 continuous, etc., we are going to start with discrete, discrete. So we're going to have discrete time and discrete random variables recorded in discrete time. And we're going to spend quite a lot of time in that regime, maybe the first half of the semester. So every time I set something up in an example, I'll say, these are discrete random variables and the sequence is in discrete time. But after maybe 2 classes, I'll stop saying that. That should be your assumption until it is stated otherwise. So a sequence of random variables might be time index starting at time 0 for like an initial value. We use the convention that random variables are always capitalized. And so we have a whole collection. That's a stochastic process. And if we want to write the whole collection at once, we would put x sub n in parentheses and possibly out here put what the index range is. But because we write that so much, we'll probably end up writing this more often and leaving the indices off. But that is a stochastic process that refers to the entire collection, whereas xn is a random variable that refers to the value of the process at time n. So let's try to envision such a process. I'm going to put time down here on this axis and the state space for the random variables. They have to live on some space. For example, maybe they all take values in 1 through 10, integers only. Just because they're discrete doesn't mean they have to be integers, but maybe they take values 1 through 10. For a stochastic process, you need the state space to be the same for all of the variables. So if x0 for some reason can only take on the values 1 through 3, then you assign probability 0 for the rest of the values 4 through 10. And we call this a state space. And we're going to denote this by a capital S. And so when you say flip a coin, the outcome is random. Maybe even a fair coin. It's a random variable. You don't know what it's going to be. Once you flip it and you get tails, you have observed it. You have a realization of your random variable. So if we observe or have a realization of this process at time 0, we will have a point. And then at time 1, if we observe the process and have a realization, we will be potentially somewhere else. So the process will have moved like this. When you start stringing together a lot of realizations of the values in a stochastic process, you have what is known as a sample path. So sample path just means an observation or realization of a process over a period of time. So let's also sort of generate a realization at time 2. Maybe the process goes here. And let me do one more at time 3. Maybe it goes here. I didn't mean for it to look the same each time. So this is a realization again of a stochastic process. And when we have a Markov process, I will formally write down the definition, but right now let's just do it in pictures. When we have a Markov process, where you go in the next time step depends on where you are at the current time step and some kind of probabilistic, some kind of distribution of values. So let me get rid of this up here. I'm going to make like an axis here at time 4. And for my discrete state space, maybe the values are here. And given that I'm at this state, doesn't really look like it hits one of those values, does it? But given that I'm at that state at time 3, where I go at time 4 is going to depend on some distribution, which I'm going to represent with a histogram, a sideways histogram. So maybe I will go to this point next with probability given by the area of this bar, whereas I will go to this point next with a smaller area, although that looks thicker, but it's not supposed to be. Maybe I'll go to this point with some probability equal to this area, and so on. So there is some distribution there. And from this drawing, it looks like we are most likely, when we are here, to end up here. But we can end up anywhere. There's probability involved. And this distribution can and likely will change its shape based on where we are here. So maybe if we were at a lower value, the whole distribution would end up here. For a Markov chain or Markov process, the idea is that the distribution here only depends on where you are here and doesn't depend on these. Well, that doesn't make sense to say it doesn't depend on those, because where you are here depends on where you were here, depends on where you were here, and depends on where you were here. So it's really expressed in terms of conditional probability. Given that this value is known, you know how this distribution looks, and you can simulate the next value without having to know these other values. So it's really that the value we're going to get at time 4 is conditionally independent of these once this one is known or given. That's the Markov property, and I'm about to write it out more formally. So here is the definition. I'm going to let S be a discrete set of values, which is going to serve as the state space for a process. And then the discrete time stochastic process, xn, as n goes from 0 to infinity, is a Markov chain if. So here's our definition of a Markov chain. The probability that the process at time n+1 is in some state j, or is equal to some state j, given at time n, we were equal to some state I, at time n-1, we were equal to some I n-1, down to at time 0, we were equal to or at state I0. This needs to be the conditional probability that xn+1 is j, given xn is I. So you can see that kind of short memory kind of thing. Again, I'm not saying this variable is independent of these, but it is once this is fixed and known. So we have this so-called conditional independence. And this has to hold for all time steps, in this case, n equals 0, 1, 2, etc. And for all states I0, I1, up through in minus 1, I, and j in the state space. So I'm going to write is an element of S. There's one final technicality to this definition, and that is whenever this has to hold only if these conditional probabilities are defined. So what does that mean? Imagine a process where at each point in time, you can either stay flat with some probability p or go up one with some probability 1 minus p. So those are the only two options. As long as that's the rule, then that is a Markov chain or Markov process, because where you go next depends on where you are. You're either going to stay where you are or you're going to be one more than where you are. And so this process is non-decreasing. And so I could talk about maybe on this right-hand side, the probability that x8 is 5 given x7 is 4. In fact, if we stay where we are with probability p and we go up by 1 with probability 1 minus p, then this is 1 minus p. But if I look at the left-hand side, if I put together something like the probability x8 is 5 given x7 is 4 and x6 is 9 and x5 is 3, etc., this can't happen because the process can only go up or stay flat. And so if I can go, well, maybe not in this one because I go one step at a time, but even if I could go from 3 to 9, I couldn't go back down. And my point is that this side doesn't make sense. And you may recall that a conditional probability, the stuff after the given line ends up as a probability in a denominator, and that probability will be 0. So this entire thing is going to be undefined. But this one was defined. So they're not equal. Does that make it not Markov? No, that's where this comes in. We only need the equality if both sides make sense. Okay, so we're going to be doing a lot of conditional probability every day, all the time. Markov chains are defined in terms of conditional probability. I did go back and say process versus chain. The word process is technically more general, and chain is usually reserved for discrete time. You can think of the values kind of chained together, but no one cares if you call it a continuous time process. Well, a process, because that's general, but no one cares if you use the words wrong. Okay, so because we're going to do a lot of conditional probability, I'm going to do a very quick review, especially because it was in the last video. So you may recall that if you have events A and B, your intro to probability course or whatever you had before this was likely event driven. So these might be that I roll a die and A is the event that I get a 5 and B is the event I get an odd number or something like that. And then we can talk about the events A union B, intersect B, and so on. And we can also talk about the probability that A happens given that B happened. So this is conditional probability. This is read as given. And if you're not familiar with conditional probability, go back to the first video. I make an argument with Venn diagrams that I think would be illuminating for you. But basically, we know that B happened, and then within B, we want the proportion of times that A happened. And so this is the probability that A and B happened versus the probability that B happened. So that's how we define conditional probability. Now, in this class, we're not really going to have events. We're going to have random variables. And if we start with discrete random variables, we can talk about things like the probability that x equals some value little x. Remember, we can't talk about that for continuous random variables because, well, we can, but it would always be 0. So it's totally uninteresting. And we can define the conditional probability that some random variable x equals x, given that a random variable y was observed to be y. We'll write this as the probability that x equals x and intersection y equals y. But when talking about random variables, and is denoted by a comma. So that probability right there is read as the probability that x equals x and y equals y. And then we put that over the so-called marginal probability that y equals y. So this is how we define conditional probability for random variables. And what we're going to have in this class is a lot of things here and a lot of things here, like a whole sequence of things potentially on both sides. And so there are going to be many ways to break up, to group things, to say I'm intersecting this with this, or I'm intersecting this little part with all of this. That doesn't really make sense. So let's wait till we get to an example. Before the examples, you know that for a probability mass function such as this, if we sum over all of the values little x, we're going to get a 1. And if you sum over x, the probability that x equals x, given y equals y, you're just doing probability in what I call conditional land, or the universe where y equals y. And so it's really just the probability that x equals x in this conditional land. And so this is going to sum to 1 as well. And all of the usual laws of probability are still going to hold in conditional land. Okay, so suppose that we want to compute the probability that x equals x, and suppose that it's more convenient to bring in another random variable, y. So in your basic intro to probability course, you probably had urns or boxes or drawers with colored balls in them. And someone said, you have 3 urns and you draw a ball from urn 1 with probability 1/2, urn 2 with probability 1/4, and urn 3 with probability 1/4. And urn 1 has 3 red balls and 7 green balls and whatever. And so you randomly select an urn according to those probabilities, and then you go in there and select a ball completely at random. And the probability you get a red ball, well, at first that might seem hard, but it would be really easy if you knew which urn you were in. So you may recall conditioning on which urn you were in, which was probably called the law of total probability back when you learned it. We're going to condition on another random variable y. We're going to bring another variable in to compute this probability for x, because sometimes it's convenient. So if I look at the joint probability that x equals x and y equals y, and sum out over all the y values, then we get back to this so-called marginal probability. See video 1 if you want to know where the name marginal came from. But we do know that the probability that x equals x, given y equals y, is equal to the probability that x equals x and y equals y over the probability that y equals y. So that's a definition of conditional probability. And we can write this joint probability as this times this. And I call that unraveling the definition of conditional probability. So going back up here, we've got the sum over y of the probability that x equals x, given y equals y, times the probability that y equals y. Just unraveling the definition of that conditional probability. So once you get used to this calculation, you'll just go straight from the left side to the final expression. This is called, actually, let me give that a color there. You'll just write this directly without going through that intermediate step. This is called computing a probability for x by conditioning on the value of y. So you're going to see maybe in a homework assignment or something, a hint to do this problem, condition on Z or something. And it's this sort of procedure. I want to say trick, but it's not a trick. It's not, there's no tricks here. It's just cool math. Okay, so the last review item is double conditioning. So here's where you want to compute something that's already conditional. And for some reason, it becomes easier if you condition on an additional random variable. So let's do this by conditioning on Z. Now, if this was not conditional to begin with, if we wanted to compute the probability that x equals x, this is going to be, by conditioning on Z, this is going to be the sum over little z of the probability that x equals x given z equals z times the probability that z equals z. But we don't want this, we want this. And that means that this entire computation takes place in conditional land where y equals y. And that means every probability here should have a given y equals y. So the conclusion here, or what I'm trying to say here, is that this conditional probability is the sum over z of the probability that x equals x, given not only that z equals z, but y equals y, and the order you write these down is not important, times the probability that z equals z, given y equals y. In the last video, we proved this. And again, if you skipped it and this looks intense to you, then you should go back and check it out. There's actually timestamps in the video and it will say there's a timestamp for double conditioning. I need to formalize this. Here is the definition of a Markov chain on a discrete state space and in discrete time. So I'm going to let capital S be a discrete state space. And then the discrete time, stochastic, what? The discrete time stochastic process, xn with a bracket, on, I mean living on, taking values on S, is a Markov chain. So we have an idea sort of from pictures, but if the conditional probability that xn plus 1 is equal to j, given xn is equal to I, and xn minus 1 is some I n minus 1, down through x0 is some I0. If this is the same as the conditional probability that xn plus 1 equals j, given xn equals I. So because we know the value of the chain at time n in this given part, we don't need the further back history. Now this has to hold for all n time steps 0, 1, 2, etc. And for all these states, right? We've got I0, I1, In minus 1, I, and j. I could have called this, of course, In and In plus 1. But since these are the sort of two letters we're going to be keyed in on, I didn't want to keep that sequence notation there. But these need to be in the state space S. That's the definition. And there's a little caveat. This is going to be wherever these conditional probabilities are defined. So for example, I mean, what does this mean? Suppose that we have some kind of process where at each point in time, we stay flat. Like, you know, where we are at time 3 is exactly where we were at time 2. We stay flat with some probability P, or we increase by 1 with the rest of the probability, 1 minus p. Right, so it's going to be some kind of random walkie kind of thing. We're either going to stay flat or increase by 1 with probability p and 1 minus p. That, as described, is a Markov chain because where you go next only, the way I've described it, it only depends on where you are. But in this case, suppose we were looking at maybe the probability that x, I don't know, 5 equals 6 given x4 is 5. That is an increase of 1 unit between those time steps, and that probability in this example is 1 minus p. We stay flat with probability p, and we go up by 1 with probability 1 minus p. So on the left side, if the given stuff is messed up, so if we have the probability x5 equals 6, given x4 is 5, and x3 is 7, and x2 is 1, x1 is 0, and x0 is 0. We have a problem because this can't happen because the process is non-decreasing. It either stays flat or goes up. So it can't go from 1 to 7, and then it can't go back down to 5. So this doesn't make sense at all. And for a conditional probability, the stuff after the given line is in a denominator. So the probability of that stuff is going to be 0. And so the left-hand side, should try to fit an equal sign in here, equals, the left-hand side of this yellow equation is undefined, and the right-hand side is 1 minus p. But because of this caveat, it's actually okay. They only need to match if both sides are defined. Okay, so we're going to actually have some worldly examples involving umbrellas, but just as a computational example, a couple of things. So one is that the probability that, say, x4 equals 3, given x3 is 1 and x2 is 5. Now, this is not the increasing chain example. This is just, suppose we have a Markov chain. Let me write that first. So suppose that the collection x0 on up is a Markov chain, and it's going to be on a discrete state space. You should always assume that. We're going to be doing that for maybe half the semester. So I'll let you know when we start to move to continuous things. But if we have, I don't know, some values here, we know that this is equal to this shorter conditional probability. That is the Markov property. By the way, I just want to write this in case anyone's lost on such a big conditional probability. This is defined as the big intersection of all of these. x2 equals 5, x1 equals -2, x0 equals 3 over all of the stuff after the conditional line. So this is like A, and this is like B. And so this is the intersection of A and B, and this is B. So for a Markov chain, we know that we have this. And the definition that I gave you is actually much richer than it might look. We can have missing values on the right-hand side. So I should write this up here. We know, if we know the definition of a Markov chain, but I claim that the probability that x4 is 3 given x2 is 5. So you see how I've skipped x3. And let's also skip x1. X0 is 3. Another thing I want to say is when I write something, an equality that's due to the Markov, I'm going to put like an MP over an equal sign when I'm using the Markov property. So I claim that the Markov property here says that this is the conditional probability that x4 is 3 given x2 is 5. Even though that's not quite how we defined it, because we defined it with an n plus 1 and an n right below it, and all of the values below that. So I claim this, and let's prove it, because this is what we're going to be doing a lot of, conditional computation. So this would be a good practice in a sort of big conditional computation. And from now on, after we prove it, you can just use the Markov property to say where we go at time 4. Yeah, if we knew where we were at time 3, it would only depend on that, but we don't. So all we really need to keep, though, is the last time step piece of information. Let's prove it. So this Markov chains are usually time homogeneous, and that's mostly what we're going to be studying. And that means that where you go next depends on where you are, but it doesn't matter what time step you're at. So this could actually depend on n. But for a time homogeneous chain, it won't, and they will be constant. I'm not sure if I answered that, so let me know if I didn't. So showing this is, important to follow, because maybe we don't care about this particular calculation, but this is kind of how they all work. So I'm going to start with the left-hand side, the probability that x4 is 3, given x2 is 5, and x0 is 3. And I'm missing not only x3, but x1. So we can put it in on the left-hand side if we marginalize it out, right? So if this was part of the review, but like the probability that some x equals x is the same thing as the sum over all y's of the probability that x equals x and y equals y. This is a marginal probability and this is a joint probability. I'm going to do that right now in conditional land. So I'm going to say x4 equals 3. x3 is some x, or you might call it lowercase x3. x1 is some y. I'm going to stay in conditional land. So x2 is 5 and x0 is 3. And then I'm going to sum over all of the possible little x's and little y's, and that sum goes over whatever the state space is. So just like a joint probability, summed over one of them gives you the probability of the other one. If you have a 3-way joint probability and you sum these out, that'll get you back to just this probability, and it all works in conditional land. Okay, so next I am going to rewrite this by, I don't know how much I should review again. So the probability, there's a tiny bit of review over here. Since the probability of A given B is the probability of A intersected with B over the probability of B, that means that the probability of A intersect B is the probability of A given B times the probability of B. And I like to call this unraveling. I'm unraveling the definition of conditional probability. So I'm about to do that now. And so these are like intersections. This is like A, this is like B. So I'm going to write the intersection probability as A given B times the probability of B, but I'm going to stay in conditional land at all times. And that means that this is going to be the sum over X, the sum over Y, the probability that X4 is 3 given. So I'm going to move these guys to the other side, and I'm just going to write them in order because it looks nice. So x2 is 5, x1 is y, and x0 is 3, right? So again, A intersect B, I get A given B, but I stay in the conditional land where these are true. And then I have to multiply by the probability of B also in that conditional land. So times the probability that x3 equals x and x1 equals y, given x2 equals 5 and x0 is 3. Okay, so just it is this. I'm not going to do it in slow motion, but I'm just going to write one thing. It is this idea of unraveling. Is raveling even a thing? No. Unraveling the definition of conditional probability, but we are staying at all times in some land where probabilities are already conditioned on another event happening. So that's what we just did in a bigger, more convoluted setting. So check this out. The first probability here, that's not a color you can see. I now have the entire history on the right-hand side, so I can use the Markov property to knock off these three guys. And I'm going to do that. This is equal by the Markov property to the sum over x, the sum over y of the probability that x4 is 3, given x3 is x. And I have the other stuff sitting here. Probably you would simplify this all at once, but for our first time through, I'll do this in some stages. All right, so that was the Markov property. I want to rewrite this so that the history is in the right direction. So I want to leave the x3 over here and move the x1 to the other side. And so this is going to equal the sum over x, the sum over y. This probability is just going to sit here. And then this is going to be the probability that x3 equals x. I'm going to move the x1 to the other side. I'm going to write these guys in order, though. Not that you have to. So I moved the x1 over, and then you have to multiply by the probability that x1 equals y, staying in that original conditional land. So I did kind of the same thing again. I have this intersect that, and I wrote it as the probability of this given that times the probability of this, but it was all in this conditional space. Definitely check out, if you haven't, in the first video, the section on double conditioning. That's what we're doing. Awesome, thanks. So this probability here, we've got all the history, right? So we don't need this or this by the Markov property. And so I'm going to write that by the Markov property. I've got a sum over x. Sorry if this is, I don't know, I think it's probably boring some of you, but not all of you. Some of you might even be panicking. You'll get used to it. We're going to do a lot of this. So I'm going to use the Markov property to bring this one down, right, to just the probability that x3 equals x, given x2 equals 5. And the other probability is still sitting there. Now, don't worry, I'm not going to just do the trick again and again and again. We can actually take care of that term because the inner sum is with respect to y, and there's no y here and there's no y here. So both of those terms can come outside the y sum. And so when you sum, I'll just give it its separate line. When you sum over y, the probability that x1 is y, given x2 is 5, and x0 is 3, you are just summing a bunch of probabilities for x1 in conditional land. And that's going to sum to 1. So going back up to the big calculation, we're left with the sum over x of the probability that x4 is 3, given x3 is x, times, I have no sense of spacing, times the probability that x3 is x given x2 equals 5. So what were we trying to do? We are trying to start with this and show that it's equal to this. We got down to some weird expression, and we could power through until we get what we want. But I think it's maybe easier to say, on the other hand. So if we start with, I'm sorry about all the scrolling, x4 equals 3 and x2 equals 5. If we start here and do the same kind of thing, we can get down to the same expression. So I would start this off by saying I'm missing x0, x1, and x3. Maybe there's probably an easier way to do this, but yeah, I mean, just following what we did, that's certainly one way to do it, is to sum over a bunch of values. And that would be putting, I'll just write the first line. Putting in x3 is some x, and x1 is some y, and x0 is some z. And that would be all given that x2 is 5. So you just stop. Given x2 is 5. So on one hand, I realized that this stuff is new and there's a lot of stuff going on here. But I don't think doing that again is going to be illuminating. I really, unless you want to see it, I would try it if I were you. And if you can't get there, then let me know and we can do it. I could do it in class or an office hour. It's just the same sort of thing again. And although we need a lot of practice, this is tedious. And so you just go and you should get down to this. So that's how you would prove it if I would finish the second half. That's how you would prove that starting with this is the same as this probability. And you get that from the Markov property. And so I don't need the previous time step. I just need to use the last given time step. Okay. So yeah, let's go back to one of the questions from before. And that is about the transitions. And I was saying they could depend on time or not depend on time. So for a Markov chain, xn, the probability that always appears on the right-hand side of that Markov property, the probability that xn plus 1 equals j, given xn equals I, may or may not depend on n. So what does that mean? If you're imagining the sample path, when you're at time n, if you're currently at I, the probability you go to j might be different if you move this whole thing to another time. But most of the time, it will not depend on n. That's where all the machinery is built up, but actually gets really hard. And we will see some cases where it does depend on m. So if this probability does not depend on n, so where you go depends on where you are, not where you were, and also not what time it is. The chain is called a time homogeneous chain. So this is the bulk of what we're going to be working with. And you should always assume that the process is time homogeneous unless explicitly stated otherwise. We will have some examples where it's not, but mostly we will have time homogeneity. Okay, so where you go depends on where you are, not where you were. And also it doesn't matter what time it is. You're just doing like one time step somewhere. So in the case that we have time homogeneity, this is going to be constant in n. It's not going to depend on n. And we're going to set up some notation. So if the Markov chain is time homogeneous, I just said we should assume that. So I don't know why I'm writing this again. Then we're going to use, sorry. We're going to use this notation. This is the lowercase p sub ij. I know it's not clear, but when I write probability next to it, hopefully it'll be more clear. This is going to be the probability that at time n plus 1, we go to j, given at time n, we were at state I. And it's also going to be the probability that, say, x1 is j, given x0 is I, because it doesn't matter what time you're at. It's just a one-step transition probability. So that's what it's called, a one-step transition probability. And we arrange these in what is known as a transition probability matrix. We usually call these capital P, not to be confused with the other capital P. Typically, it's like a double-lined P. And this matrix is going to have a row and column for every value in the state space. So while we will have infinite matrices, I'm just going to try to make this a little simpler for this example. Suppose our state space is only 0, 1, and 2. So those are the only values the chain can take on. In this case, this is going to be a 3 by 3 matrix where I can label the rows and columns 0, 1, and 2. But again, sometimes they're going to be infinite and there's going to be some dot, dot, dot notation. And then inside you put the probability of transitioning from here to here. So that means the first row is P00, P01, P02, and the second row is P10, P11, P12, and then finally P20, P21, P22. Again, from here to here. Don't worry, we're getting to some numerical examples soon. So this is this has a property, has at least one property. Note that the rows must sum to 1. Why is that? Because let's just look at this row, focus on the row labeled 1. It's actually the second row in the matrix. Given you're at state 1, you have to go somewhere, especially if you're allowed to stay at state 1. That's also included among the transitions. So you either go to 0, you stay at 1, or you go to 2, and that's one of those has to happen. So those have to add up to 1. And so we write this in symbols as Pij. We go over all j in, so I know most of you, this is going to seem weird that I'm defining it, but right, j and this symbol means overall j in S, just in case. This has to be 1. So that's always true of a transition probability matrix, even if they're infinite. The columns, they don't have to be anything special. They certainly don't have to sum to 1. In fact, we could have a column of all zeros, and that says that you can never get to 0 from anywhere. Even if you start at 0, you will immediately move away from 0. So the columns do not have to sum to 1. By the way, if the rows sum to 1, we call it a stochastic matrix. And if the columns also sum to 1, which is not usual, but when it happens, we have it makes some computations a lot easier. So if the columns also sum to 1, it's called a doubly stochastic matrix. You don't need to remember that. I'm going to bring that up again the first time we see something like that. No, yeah, so going from 1 to 2 is P12, and going from 2 to 1 is P21, and they can definitely be different. It's not a symmetric matrix. Yeah, then we'll have like a P sub n or something, which is hard to write down. Well, unless you have a formulaic sort of transitioning. Yeah. Okay. Let's look at a totally manufactured example. We've got like those bike stands on campus where you can like rent a bike and return it somewhere else. So yeah, let's look at that. So bike, I don't know, they're not, I guess they're rentals. Rental stands or stations. Stations might be better. So for simplicity, let's assume there's 3 and they're named A, B, and C. So we've got station A, station B, and station C. And I'm going to assume that a bike picked up at station A will only be returned to station A with some probability, say 0.3. Let me make this bullets to make it easier to write. And if a bike is picked up at station A bike picked, why did I give this a whole new sentence? It will go to station B with some probability that I'm going to say is 0.5. Since I started it, I'll finish writing this. At station A will be returned or dropped off to station B with probability 0.5. And then the rest of the probability 0.2, it will be dropped off at station C with probability 0.2. Whether or not this process in real life would be Markovian, would only depend on the last piece of history. We're going to assume for this toy example that the position of the bike at each time it's dropped off is a Markov chain. So I'm going to let xn be the position, the station of the bike at drop off n. I'm just going to say time n, but time is measured by where it goes next. So certainly not continuous time. Now, to fully describe this process, I need to say, okay, what happens when you start at B and what happens when you start at C? But I don't want to write all that out in English, and you don't want to see it either. So the transition matrix, we can write like this: A, B, and C to A, B, and C. And the information we have already says that we go from A to A with probability 0.3. We go from A to B with probability 0.5, and from A to C with probability 0.2. I'm going to fill in the rest of the numbers. Where do they come from? It's part of my example, but I didn't want to write out the English sentences for that. So let's say if we pick up a bike at station B, it'll be dropped off at station A with probability 0.1. This is just given. This is part of the example. And it will be returned to B with probability 0.3. And it will be returned to C with probability 0.6. Or if in this model you want to define what time steps are, maybe it's each morning, then from B to B could be 2 things. This could be made up of actually returning it to B or never taking it in the first place. So just staying at B. Depends on how we want to define, like, what is time 1 and what is time 2. It's just an example. And let's say the last row is 0.7, 0.1, and 0.2. So normally you would put this matrix together by grabbing all these numbers from the word problem, but I only wrote out the words for A and I'm just filling it in. Hopefully everyone's okay with that. Like, where did I get this? I made that up. It's the problem. Okay. Random variables, by the way, are technically always numbers. They are mappings from a sample space of an experiment whose outcomes involve probability into real numbers. So if you're like flipping a coin, don't write this down, but you might define a random variable to be 1 if you get heads on the coin and 0 if you get tails on the coin. Technically, they are numbers, but I am going to be talking about the probability that like x at time n equals a. It's just easier. I mean, I could call this number 1, 2, and 3 if I really want it to be numbers. So I'm being a little fast and loose with notation, but let's answer some questions. First one. What is the probability that at time 1 we're in station B, given at time 0 we were in station C? This is just read off the matrix. We're starting at C and we're going to B. And so this is probability is 0.1. This is purely read off the matrix, nothing more than that. For my next trick, I want to talk about the probability that at time 8, we are at B, given at time 7, we were at C. So this is a Markov chain, which you should always assume as time homogeneous. I'm not just talking about in this course. If you're reading someone's article and they have a Markov chain, they're going to be assuming it as well, unless they specifically say otherwise. And so this is still just one time step transition. So it's the same. It's the probability of going from C to B in one time step, which is right here in the matrix. So that's by time homogeneity. Please stop me if you need to. What is the probability that x8 is, I'm going to mix this up a little, is C given x7 is C and x4 is A? So by the Markov property, I don't care what happened at time 4. By the Markov property, this is the probability that x8 is C given x7 is C, and that can be read right off the matrix. That is the C to C entry, which is right here. That's 0.2. So further back history, it doesn't matter. So how about this one? What is the probability? Oh no, got a little lag there, sorry. The probability that x2 is C and x1 is A, and let's say x0 is B. As stated, we can't do this problem because the matrix only talks about transitions and we don't know the probability that we start at B. So there's, not enough info from the matrix. Again, that only talks about transitions. We need what is known as an initial distribution. We need someone to say, this process is going to start at A with some probability, start at B with some probability, and C. So as an example, let's say the probability that X at time 0 is A is 1/2, and then maybe the other two probabilities are 1/4. So someone has to give you that in order for you to be able to answer this. And now we want to turn this into conditional probabilities because we know about those from the matrix. This is always like an intersection going to a conditional probability is what I call unraveling the conditional probability definition. But the tricky thing is you have to figure out what is your event, your set A and your set B, not to be confused with the A and B in here. I can write this as the probability that x2 is C given x1 is A and x0 is B times the probability that x1 is A and x0 is B. This is me saying, sorry about the letters, but the probability that A intersect B is the probability of A given B times the probability, times the probability, probability for B. I'm just defining this to be the event A and this to be the event B. Okay, so I can use the Markov property to get rid of this guy, because once I know where I am at time 1, where I go at time 2, it no longer depends on where we were at time 0. And in order to use the Markov property over here, I'm going to pull that unraveling trick one more time. I'm going to leave that x0 in there. I'm going to use the Markov property like all at once. But I can write this other probability as the probability that x1 is A given x0 is B times the probability that x0 is B. And so now I'm going to use the Markov property. The probability that x0 is B was given to be 1/4. And the other numbers are one-step transition probabilities, which can come out of the matrix. So if you go back to the matrix and go into the A row and the C column, that should have been 0.2. I'll check in a second. I just don't want to keep scrolling back and forth. And then if you go to the B row and look over to the A column, that was, I believe, 0.1. And then we get a 1/4, obviously 0.25, but I'm going to leave the 1/4 so you can really see where that number came from. So these are read off the matrix. And that's a number, I don't care. And by the way, in any homework assignment or exam in this class, you don't have to simplify anything. That's, you obviously just showed that you know how to do this problem by writing that down. That's my next example. So thank you for that beautiful segue. Let's do that now. I'll call this E. And to start, I don't want to go 2 time steps. So let's just look at the probability that, say, x1, because there's an easier way to go to 2 time steps than to write this long procedure out. So let's look at the probability that we are in station A. The bike is in station A at time 1. There's no transitions here at all, but we have an initial distribution. I'm still going to keep that 1/2, 1/4, 1/4. So we can condition on where we are at time 0. So when you're conditioning on where you are, you typically don't write this next line, but I'm going to do it since it's really like our first time through. This is the probability that x1 is A and x0 is some like I, where I is A, B, or C. This is really strange to be summing over A, B, and C. Right, so this joint probability, we can marginalize out to this. And the joint probability, by unraveling the definition of conditional probability, can be written as the probability that x1 is A given x0 is I times the probability that x0 is I. And again, I is going to be A, then B, then C. So if you are conditioning on where you are at time 0, you really just go straight from here to here. But this stuff was the Y. And if you want to write it out, that's great. And if you don't want to write it out, that's okay as well. But that's where it comes from. Okay, so this is, it might be more clear to you if I write out the actual 3 terms, but that's kind of long. So I'm just gonna, hopefully you'll get it. I'm going to plug in I equals A. So that second probability is 1/2. And then I'd be going from A to A. And that from the matrix was 0.3. And then for the second term, the probability that this is B is 1/4. And then I'm going to be going from B to A. And from the matrix, that was 0.1. And then finally, for C, the probability we start at C is 1/4. And the probability we go from C to A comes out of the matrix, and that is the 0.7. So yeah, to compute where we are at time 1, that probability, we could condition on where we were at time 0. And we can also do that to compute probabilities for x2. We can condition on where we were at previous time steps. But I've got a better way to do it than writing these out. So let's hold off on the x2. That's actually not true at first. The transitions are homogeneous, and that is a really good point, though. So the probability of moving from A to B is the same no matter what time you're looking at. But where you are at time 1, that probability is not the same as the time 2 probability unless you start the chain in like an equilibrium. This is going to be known. We're not there yet. Don't bother to write this down because this is so out of the blue right now. We're going to be looking for what is known as a stationary distribution for the chain. And that is if you set the time 0 probabilities to be just right, what you said is going to be true. But think of it this way, like maybe you are watching customers come into a store and I don't know, if there's currently 4 people in the store, what's the probability that in the next people that arrive, there's going to be exactly 3 more, so you'll go up to 8. Eventually, if the store runs for a long time, that's supposed to reach an equilibrium. But if you start the store with 1,000 customers versus starting the store with 0 customers, the probabilities, they have to kind of settle down. We would just have to write this out. So we will be conditioning on where we are both at time 0 and time 1, and this will be a joint probability for time 0 and time 1, and then we have to break it down like the last problems. And no, this should not be the same at time 2. So let's notice something else. I've got an F for you. This is going to be the probability that at time 2 we are at some state like B, given at time 0 we are at like state A. This is a 2 time step transition. So this is a 2-step transition. And what can we do? We need to know what x1 is. We're going to condition on where we are at time 1. I'm going to give this its own line. So condition on where the bike is. I'm just going to say where we are at time 1. So I'm going to go straight there. Usually I would put an x1 equals some value like I in here and sum over all the i's. And then I would take that intersection between the x2 and the x1 and move it over. But this is the sum over all I of the probability that x2 is B given x1 is this I that's running over all states and x0 is A times the probability that x1 is I given x0 is A. So we conditioned on where we were at time 1. And so you're probably used to this, but we did it in that conditional land. So we kept the x0 equals A everywhere. So now by the Markov property, I don't need this information over here. And both of these are 1-step transition probabilities. So let's do it. When I equals A, maybe, I don't know if I should, I'm going to write this out because it's our first time seeing this stuff. So this is going to be the probability x2 equals B given x1 is A times the probability x1 is A given x0 is A plus the probability that x2 is B given x1 is B. So we're just running x1 over the different values. x1 is B given x0 is B plus x1 could also be C. This, by the way, is the law of total probability. If you recognize it from the event kind of space. So all of these are 1-step transitions. To get, for example, this probability, I have to look at the AA entry to the matrix. To get this one, I have to look at the A to B. And so that's what I'm going to do. I'm going to fill these guys in. You know what? Let me copy that matrix. Okay, so these probabilities, the A to B is right here. It's 0.5. And the A to A is 0.3. And then the B to B probability is 0.3. and the B to B probability is 0.3. And then finally, the C to B probability is 0.1, and the B to C probability is 0.6. This sum over I was changing this value and this value, but this should always be A. Thank you so much. That is my mistake. So these, I'll put a different color in so you can see exactly where that mistake happened. This should be A. This should be A. X0 is always given to be A. We are living in that conditional space. So that's going to change these numbers a little bit. So this was the probability of going to B in 2 steps, given that we started at A. Let me just remind you. And do you see it? You see it. Well, now that we on the 4th try, I have the values right. You see it, don't you? You see the values across the A row individually multiplied by the values down the B column and summed. It looks like matrix multiplication. So can we get this from matrix multiplication? And if so, that would be awesome, because if we have more time steps skipped and a lot of states, writing it out like this is going to be hard. So that's the conjecture at this point, that we can get it from matrix multiplication. So this happens to be this turned out right here to be the A to B entry of the transition probability matrix squared, and that's what we're about to prove. So I don't think we'll get completed to that proof, but let's start setting it up. We're going to need some notation, and this is this sort of thing about these powers of the matrix. These are known as the things we're going to end up with are known as the Chapman-Kolmogorov equations. So we're going to need, as I said, some notation for a time homogeneous Markov chain. We used little pij to denote the probability of going from I to j in one time step. And now I want to use an n in parentheses in the exponent. So I'm going to just say pij super n, because it's not pij to the nth power. This is going to be notation for the n step transition probability, which is going to be the probability we go from state I at time 0 to state j at time n, and in a time homogeneous setting, so th for time homogeneous, we could be given that x at time k is I, and we'll go to some state j at time k plus n. Last thing I can say, because I'm out of time, we're going to use this notation to prove that matrix multiplication thing. But Duret, if you watch the first video, you'll see that I talked about the syllabus, and I had a book in there I recommended by Richard Duret. He uses pij to the n, and I hate this notation, because it is not, this n-step transition probability is not pij to the nth power. This obviously looks like a power. I think that's horrible notation, but you should watch out for it, especially if you're using his book as a reference. So yeah, we're set up. We've got the notation, and next time we're going to prove that the 2-step transition probability is an entry of p squared, and the 3-step transition probability is an entry of p cubed. So if you have a lot of states and a lot of time steps to skip, I just got to notice that Zoom quit. But we're going to prove that matrix multiplication thing next time on Markov chains. So thank you.